Okay, welcome back. Um, so we said Lewis structures can be used for two things. One is molecular geometry, which we just did, and polarity. So I want to do a quick review and then move right into the polarity because my last video got a tad bit long. All right, so we said that if we looked at the Lewis structure, we could take a look at the central atom and then count how many components are around it. And then we get our 5 basic families of shape, depending upon how many components that you have. We said within those families, if you substitute a covalently bonded atom with an unshared pair, then that distorts the geometry a little bit, and we could technically call them different things. Like in the tetrahedral family, one unshared pair would give us trigonal pyramidal, and two unshared pairs would give us bent. But I said not to worry about that too much because I teach it from the perspective of, again, the difference in the bond angle doesn't create enough of the difference in the chemical reactivity to say that they're different shapes. But this is the way it's taught in your book. And for trigonal bipyramidal, we said that if you have unshared pairs, make sure you put them on the equator. But you don't have to know the 3 names of the structures that are made with the unshared pairs. And for octahedral, we said to put the unshared pairs on the North Pole and the South Pole if you have to put unshared pairs on it. There are other families other than the ones that we covered. My favorite is tricap trigonal prism. And we said that if you have an unshared pair, the bond angle will be close to what the family angle is, but it's going to be a little bit less than expected. Now, there are some exceptions to that. Again, there's 14 million chemicals, so not all of them follow the rule. So, yes, water's in the tetrahedral family, but it's not 109.5. And oxygen difluoride's in the tetrahedral family, but again, it's less than 109.5. You don't have to know any of those bond angles for the ones with the unshared pairs. Just answer on the multiple choice that it's less than 109.5. Now, that last example, oxygen dichloride, the chlorine atom is so large itself that it's the electron pairs don't create enough repulsion to bend the chlorine atoms to each other. The atoms themselves repel each other more than the unshared pair, and you actually wind up with a bond angle slightly greater than the family angle, but that is an exception to the rule. When they ask you for bond angles, they're only talking about the angle between the bonded atoms, not the angles that go through the unshared pairs. For instance, in this example, if you were to go from axial North Pole fluorine to South Pole fluorine, where the unshared pair is, that's going to create a bond angle greater than 180 degrees. And we said that just think of that as the unshared pair taking up more than its normal amount of space and causing the other atoms to bend towards each other. All right, molecular polarity. We make our Lewis structure, and I would pause at this point and write this down in your notes, but make the Lewis structure. Again, look at the central atom. Now, they talk about symmetry around the central atom, so we got to be careful with that. When I say symmetry, I don't mean, for instance, advanced algebra symmetry. I'm not talking about symmetry with respect to y equals x. I'm not talking about x-axis symmetry or origin symmetry. What we mean is take a look at the components that are around the central atom. If they balance out, it's symmetric. If they don't balance out in terms of their electronegativity, then we call that asymmetric. If it's symmetric, we're dealing with a nonpolar molecule, even though it may have polar bonds. If it's asymmetric, then we're dealing with a polar molecule. For example, these two are from the tetrahedral family, and we would say that phosphorus trichloride is not symmetric because this unshared pair is not the same electronegativity value as the 3 chlorines that surround the phosphorus. Whereas in carbon tetrachloride, all 4 components are exactly the same. So this is considered symmetrical and nonpolar. Whereas this is considered asymmetric or non-symmetric, which is polar. And almost always having an unshared pair on the central atom will give you a polar molecule. Almost every single time. There's only two exceptions, and I'm going to show you the two exceptions in a little bit. All right, so examples of polar and nonpolar molecules. If you have a molecule that doesn't have a central atom, then you do what we did in the last chapter. You just look at the electronegativity difference between the two elements. I think chlorine is something like 3.5 and hydrogen is 2.2. So we would have the hydrogen be the pseudo-positive end and the chlorine be the pseudo-negative. That's a dipole. Ammonia is polar because the fourth component on the ammonia is an unshared pair, whereas the bottom, two of the bottom examples are nonpolar. Boron trifluoride has 3 fluorines surrounding it, no unshared pairs, because remember, boron is an exception to the octet rule. It only needs 6 electrons to be stable. And carbon tetrachloride is nonpolar, even though each bond is polar, because you have 4 chlorines and their vector force arrows would cancel each other out. You don't have to add vector arrows at this level. Whereas if you take the 4 components around chlorine and make one of them different, the chlorine is the most electronegative element in that molecule, and the electron charge cloud shifts towards that chlorine, making the chlorine part pseudo-negative, and the 3 hydrogens become the pseudo-positive end. So we would say that that is a polar molecule. It's asymmetrical. And these are just the same examples showing the vector arrows. And again, when we're looking at bonds, electronegativity gives us different polar versus nonpolar bonds, but if those vector arrows cancel out, then you wind up with a nonpolar molecule. In this case, the vector arrows don't cancel out. If we add them, if you've had this in physics, if you haven't, don't worry about it, we would add them head to tail, like that, and then we would create a resultant vector. Darn it. We would create a resultant vector, and then this vector would tell us that the hydrogens are the pseudo-positive end, the oxygen's the pseudo-negative. Again, I'm just showing you the physics of it. You certainly are not required to draw vector arrows. Another way they like to display things, since I have to do everything in multiple choice now for the most part, I'm going to try to throw in an FRQ on this, but we'll see what happens. They like to show different color-coded areas. With red, that means electron surplus. So red, this would be pseudo-negative, but it's also pseudo-negative on all sides. Whereas this one, the blue, represents pseudo-positive, and the red areas represent pseudo-negative. So the second one is polar because there's a distinctive opposite end. Here's the 2 exceptions to the rules where you have an unshared pair, but yet this is nonpolar. If all of your, in trigonal bipyramidal, this first example, if all of your unshared pairs are around the equator, the forces cancel each other out and you wind up with nonpolar. I try to avoid putting that sort of thing on the test though, because it is advanced. And for octahedral, if you have 2 unshared pairs, one will take the north pole, the other one will take the south pole, and those unshared pairs will cancel each other out. So those are the 2 exceptions. But again, 95% of the molecules you're going to do at this level, if there's an unshared pair on the central atom, we're dealing with a polar molecule. All right, this hybridization thing. Hybridization is a theory of bonding, and what it said was that if you have, for instance, 4 valence electrons, like in carbon, carbon's configuration is helium core 2s2, 2p2, and what would happen is the electrons would move around and change energy and blend together to create 4 bonding orbitals. And so since one of the components is an S structure and the other 3 are the p orbital structures, they said, well, we're going to call this an sp3 hybrid. Now, it turns out this theory of bonding was disproved. There are some aspects of it that contribute to the current theory of bonding. The current theory of bonding is called MOT, molecular orbital theory. And what it does is it treats the electrons as though they're waves, and you can bond 2 different ways. You can bond by adding the waves together and having them add constructively, or you can bond by having them cancel each other out and do destructive interference. We're not going to get into that. That is second or third year college. So why keep hybridization theory if this is not what actually happens? Well, hybridization, again, there are components of it that are used in MOT, and the two things that hybridization is good at is explaining the existence of double and triple bonds, and it does a good job of predicting geometry. Okay, for instance, if you have something that's tetrahedral with an unshared pair like nitrogen, nitrogen's in group 15, so it has 5 valence electrons, and 3 of the valence electrons are used to create bonds with the hydrogens. And then the last 2 of the valence electrons are used to create the unshared pair. So we would say that this is an sp3 hybrid. Even though it has 5 valence electrons, it only has 4 areas of space. Now the way they describe the areas of space is that the first area is always called S, and then the next 3 are called P, and then the next 5 areas are called D. So if you have 2 areas of space that you have to accommodate, like in trigonal planar, then that's called an sp2 hybrid. If you have 6 areas of space to accommodate, this would be called an sp3d2 hybrid. We'd have to use the d orbitals to create the expanded octet. And that part of the molecular theory, molecular orbital theory, is used from hybridization. So 6 components. 1 of them is an S, 3 of them is a P, and 2 of the orbitals are Ds. So we call it an sp3d2 hybrid. The number of areas dictates the term for the hybridization. So again, if there's only 2 areas of space, if we have a central atom and then it's connected to 2 other atoms, there's only 2 areas of space there. We would call that an sp hybrid. It's really very simple. Now, with double and triple bonding, I said that in the last video, components of space. A double bond only takes up 1 component of space, even though it's 2 bonds. And a triple bond only takes up 1 area of space, even though it's 3 bonds. It has to do with the way things overlap. So a couple of things. First of all, anytime you see all single bonds, you're going to, and it follows the octet rule, it's going to be an sp3 hybrid, 4 areas of space. However, if one of the bonds is a double bond, the double bond only consumes 1 area of space. The other 2 single bonds occupy the second and third area of space. We're going to call it an sp2 hybrid. And then with a triple bond, there's only 1 single bond, so that's a total of 2 areas of space, a triple and a single. We're going to call that an sp hybrid. Now there are 2 ways of creating covalent bonds. One is called sigma overlap, and they say that they lie directly on the same bond axis. I'm going to draw that in a moment. The other is to create what's called a pi bond, and pi bonds are parallel overlap. They wrap around sigma bonds. Okay. So here's my little symbol sigma. And what they mean by a sigma bond is we're going to take the first atom and we're going to overlap it end to end with the second atom, and we would say that this is a sigma bond. Now, the thing about a sigma bond is sigma bonds are low in energy. So nature tends towards stability. Sigma bonds tend to be really stable. The problem with sigma bonds is they consume a lot of space. Now, a pi bond is what we call parallel overlap. So let's say we have a nucleus of one atom, a nucleus of another. What we're going to do is we're going to use the p orbitals, and they're going to overlap each other this way, and then the electrons are caught in the area of overlap. This is side-by-side overlap, where sigma is end-to-end. Another term for side-by-side is parallel overlap. And the good thing about pi bonds is that they only consume a small amount of space. They wrap around the sigma bonds. The bad thing about pi bonds, in order to create them side by side, you have to get the two nuclei close together, and that creates a lot of repulsion. So pi bonds tend to be high in energy, so unstable, but they are very space efficient. So a couple videos ago I said there's no such thing as a quadruple bond. The reason why is there's just not enough space for 8 electrons in between two atoms. There's enough space for one sigma bond, maximum, and there's enough space for pi bonds to have 2 maximum pi bonds. So that's a total of 3 bonds. Now the first bond is always going to be sigma because nature tends towards stability, low energy. And the other 2 bonds will be high energy pi bonds because there's only enough space for 1 sigma bond. You can't have 2 sigma bonds between the same 2 atoms. Okay, so what fun. So a double bond is always a combination of 1 sigma and 1 pi. A triple bond is always 1 sigma and 2 pi's. But remember your definition here. A double bond is 4 electrons, 2 pairs. A triple bond is 3 electrons creating the connection, 3 pairs. So here's an example of all single bonds. If you have single bonds, then you have all low energy sigma bonds. So if this was connected to a hydrogen, and this was connected to a hydrogen, and another hydrogen, we would have the compound C2H6, which is ethane. Remember methane, ethane, propane, butane, butane, whatever. So this is ethane, and ethane would have a total of 7 sigma bonds. 3 for each of the hydrogens connecting to a carbon, and then the 7th sigma bond would be the connection between the 2 carbons. Now, ethylene, or what's actually called ethene in the new nomenclature, that has a combination of sigma and pi bonds. Each hydrogen is connected by a sigma bond, and the carbons are connected by a double bond. So one is sigma and one is pi. So what they'll ask you to do on a test is they'll say, okay, here's the structure. How many sigma bonds, how many pi bonds do you have? And here we would say that, better use a better color than that. Here we'd say that we have a total of 5 sigma bonds. 4 going to the hydrogens and 1 creating the double bond. And then here we have a total of 1 pi bond. And in a triple bond, you have a sigma and 2 pi. So in this compound, right here, they would say, all right, how many sigma bonds, how many pi bonds? Well, we have a sigma bond between each of the carbons and hydrogens, and then we have a sigma and 2 pi's to create the triple bond. So we would say that we have a total of 3 sigma bonds, and we have a total of 2 pi bonds. And that's all they want you to do with it at this level. So here's an example. Go ahead and try it. How many sigma bonds, how many pi bonds do we have? And then, of course, come back and check your answer. Sigma, 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 sigma. And then here we have a sigma and a pi. Here we have a sigma and 2 pi bonds. So we have a total of 6 sigma and 3 pi's. And that involves a benzene structure. Okay, whenever they have these structures where there's like these hexagons, they assume that you know that there's a carbon in each of these vertices. I won't do that to you on the test. So go ahead and try this one. How many sigma bonds? How many pi bonds? Right, sigma, 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 sigma. Right, we got a sigma, and then with the double bond, a sigma and a pi, a sigma. We have a sigma and a pi, another sigma. And then here we have a sigma and a pi. And then on this last one, which is called a, it's called a nitrile group, sorry. A sigma and 2 pi. So now we got to add all these up. So what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like 12 sigmas. And a total of 1, 2, 3, 5 pi. Let's just check that real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 1, 2, 3, 5 pi's. Okay, that's correct. That's all you have to do with that. And resonance and isomers, I will do on the next set of videos. So thank you very much.